Now we want to talk about linear correlation. So what we're looking at here are two scatter plots, and the left graph is talking about the height and weight for women in statistics, as well as the right graph over here. And I hope you start to notice that both of these graphs look pretty much identical. If we wanted to talk about the direction of the dots, we could say that they might be falling in some sort of, while it's kind of scattered and not quite nice and tight dots, it is still moving in some sort of linear pattern and in a positive direction here. And I could say the same thing for the second graph over here with the dots in blue, that we are looking at a pattern where it is somewhat linear in fashion, and again, it's moving in a positive direction. So if I'm showing you two graphs that look like they're doing the same thing, what's the differences in the two graphs? We're both talking about, or both the graphs are talking about, the height and weight for women in statistics. Notice that the graph over here on the left, the one that's in red dots, is talking about weight and height, but here we're looking at kilograms and centimeters. So this graph over here is indicating the weight and height in the metric system. And if we turn our attention over here to the dots that are blue, notice that the weight and height over here are given in the US system. So what do we notice? We notice that it doesn't really matter as far as the direction and the shape of our scatter plots. As far as units are concerned, they're both telling me the same story. So I don't care if I am talking about the relationship between height in centimeters and weight in kilograms, because it's the same relationship, height and weight in pounds. And that makes sense, right? It doesn't matter how tall I am in inches and pounds, because it's going to be the same exact value whether I measure myself in centimeters and kilograms. All of that's to say that when we want to talk about a measurement for the relationship here between height and weight, which is basically saying that as your height is increasing, your weight would be increasing as well. Again, that's kind of makes sense to us. What we want to discuss right here is what is the strength of that relationship. And that brings us to what we're going to call the correlation coefficient. Now, the correlation coefficient, we're going to use the variable r to indicate this idea, that this correlation coefficient. And what I want you to understand is that r is actually going to be a value that we use to measure the strength of the relationship between the two variables, between our two quantitative variables. So we're going to end up with a number, a quantitative value that I can actually use to be able to talk about the relationship between these two variables being either strong or weak. Now you see up here, I've given you the formula for the correlation coefficient, and I don't ever ask you to actually calculate by hand the correlation coefficient, but I put it up here so that you could understand where this is coming from. Like, how is it calculated? Remember from chapter 3, we identified z-scores as the number of standard deviations away from the mean. So z-scores had to do with standard deviations and means. And you'll notice here that to calculate this relationship between my variables, this correlation coefficient, I'm going to take the z-scores for my x variable, the z-scores for my y variables, multiply them together, sum them up or add all of those products together, and then divide by the sample minus 1. Now, again, I'm not going to ask you to calculate the correlation coefficient by hand, but this brings us to the idea that what do we remember about z-scores from chapter 3? Hopefully, you remember that z-scores, standard deviations, and means are all not resistant to outliers, right? They're easily influenced by outliers. And therefore, because z-scores are going to be easily influenced by outliers, and we're using z-scores to calculate r, that implies that r is also going to be easily affected by outliers. So before we move on, we want to make sure that in order to use the correlation coefficient, we have a couple of assumptions that must be true. First of all, we want to make sure that our scatter plot is showing us that we are looking at a linear relationship between these two variables, and the two variables must be quantitative. So both the variables, the one off of the x-axis and the one off of the y-axis, need to be quantitative. Also, we want to make sure that the scatter plot we're looking at is reasonably straight. So you want it to, again, be linear in its relationship. And then finally, we just need to make sure we understand that there any outliers that are on the scatter plot could affect the value of my correlation coefficient. So having said that, let's talk about some of these properties that we see when we are utilizing this correlation coefficient. The first idea is that our r value, the correlation coefficient r, is always going to be between the numbers -1 and +1, including negative and +1. The closer my r value is to that positive or -1, we would indicate that that is a strong relation. However, the closer r is to 0, we would say that there is no relation. Now just remember though that when you have r close to 0, it doesn't imply that there's no relation, it's just implying that there is no linear relation. So still, if it's close to 0, we're going to say no, it's no relation, no linear relation. Close to positive and -1, we have a strong relation. We also need to understand that that linear correlation coefficient is unitless. Now this makes sense if you think back that we used z-scores in order to calculate r. And from a previous chapter, we understood that z-scores are unitless as well. And as we mentioned in the previous slide, our correlation coefficient is not going to be resistant to outliers. So let's look at a couple of images here so we can identify this idea of strong versus weak R values. Starting in the top left-hand image, we notice that this graph right here, or this scatter plot right here, you'll see that all of these points are lining up on a nice pretty little straight line. We would have an R value that is positive, and because it is indeed a line, that's the closest you can get to 1 to show us a linear relationship, then we would say that the R is equal to 1. Now this is a perfect world. This is definitely not the real world, but we start to notice then as we move from graphs B to C, notice that the scatter plots are starting to fall apart, if you will. We still have a linear and a positive linear relationship, but as the graph or as the scatter plot is starting to disperse, notice that the R value is getting closer to 0. So here in graph B, we see that the R value is somewhere around 0.9, but when we move to graph C and the points are much more spread out, we are already down to an R value of 0.4. All three of these are indicating a positive direction, and therefore their R values would also be positive. Now we turn to a negative relation. Notice that the R is -1, so we have this perfect straight line, so that's going to be that -1 value. And again, the direction, because the R value is negative, it is going to imply that we have a negative direction for our interpretation. We can see here for graphs E and F a similar concept as we saw above, that as the points of my scatter plot start to disperse, the value of the R is going to get closer to 0. So here we have a -0.9, so it's pretty close to that perfect -1. But then again, as we move over here, notice that these dots are all starting to spread out and we're back down to a negative 0.4. So that negative value is indicating the direction that the line is falling. And then these last two are showing us what it looks like when you have an R value that's close to 0. Here in graph G, you'll notice that this doesn't look like anything. It just looks like a bunch of dots up there. There's no definitive shape or no definitive linear shape that you can identify. So we would say that this has an R close to 0. However, in the very last graph right here, I have something that looks like a curve. Now, I could create an equation that represents this curve, but that's not what we're talking about here. We are actually using an R value to identify linear relationships, and it's pretty clear that this is not linear. So therefore, the correlation coefficient, the linear correlation coefficient R, would be close to 0. And a final note about those terms that we're using for a strong association, moderately strong, or even a weak association. It's really kind of it depends on, let's say, your degree. So just be aware that for one particular study in a, let's say in one field, you might have a R value of 0.7, and that might be a strong relationship for your correlation or strong correlation for your two variables you're looking at. But then if you turn around and looked at a study in, say, a different field, people or your R value might be considered strong only if it's going to be maybe at 0.9. So I have a daughter who is she has a dual degree. She has a bachelor's in chemistry, so in the sciences, but she also has a bachelor's in criminal justice, which would be in the social sciences. And she would attest to the fact that in the chemistry world, when they were creating these R values and looking at the correlation between two variables, they were looking at things that were 0.9 and above, and that's when they needed data to be considered strong when you had that R value of 0.9. However, she said in her criminal justice studies, they would look at something and they would be perfectly okay with an R value of something around 0.7. That would be considered strong for them. So you can see that it really is kind of dependent upon your area that you're studying in to determine what number is going to indicate strong, moderate, and weak.